Hello, everyone. Today we go towards homework 8, the tensor product and complexification and things related to that. That's a bit more abstract than the things we've seen before. So rather than maybe just solving problems, I would try to explain the notions and concepts, and hopefully we would spend some more time on that. Okay, so let's start with tensor product. I know that you are familiar with this concept, but let's think a little more about this. Tensor product. Okay, so for ordinary numbers, real numbers or complex numbers, we know we have addition and we have multiplication, right? Kind of the same thing is correct for vector spaces. So suppose V and W are two vector spaces. For simplicity, assume they are two finite dimensional vector spaces. So for example, V is some n-dimensional vector space and W is some m-dimensional vector space, okay? We have the product of these two vector spaces, which you are familiar with. This is just the pairs of elements like V and W, where the first vector is inside the first vector space, or n-dimensional vector space, and the second vector is in the second vector space we have here, right? And the point is that the dimension of this vector space, V times W, is the sum of the dimensions, right? So there are different notations. Sometimes we use this product, as you can see here, V times W. But also sometimes people use V plus W. But it's plus inside a circle. So it is a plus inside a circle. And this might be a better notation, because as you can see here, really when we have two of these spaces, if we look at their product, or what we call here as direct sum, the dimension of the space we end up with is the sum of dimensions of each of them. So it seems it's an analogy. It's analogous to addition of two numbers, but for vector spaces, right? Because here also we have the sum of dimensions. So sometimes that's why I might prefer to use direct sum. Great. Okay. Now, as you might know, there is another notion which is more similar to product, and that's called tensor product. So for any two finite dimensional vector spaces V and W, which here we are assuming all these spaces are defined over the same field, for example, R or C, there is another vector space called the tensor product of V and W, V tensor W. And this vector space, the point about this one is that the dimension of this tensor product vector space of some n-dimensional and some m-dimensional vector space is n times m. So it's kind of more like the product on vector spaces somehow, right? So how can we think about this space? You see, first, usually we tend to think about these spaces formally. For example, when we talked about the direct sum, or, well, which is the same as product of two vector spaces, We said this is just pair of vectors like this, like what you have here. Just pair of vectors, where the first component comes from the first vector space and the second one comes from the second vector space, right? And then, so first we represented, we told you what are the elements of this new vector space. Okay, and then we defined what is the addition, right, on this vector space. And then we defined what is the scalar multiplication. So there are three things we should do. We said what are the elements, and then what is the addition, and then what is the scalar multiplication. Right. So for tensor product, we should do the same thing. So when we have tensor product of two vector spaces, the elements, they are linear combination of elements of this form. So linear combination of elements like V for some vector V inside the vector space V, and some other vector space W inside our other vector space. And then we just use this notation of tensor between them. So it's just a notation. At this point, it doesn't have almost any meaning for us above this notation, right? It's just like putting V and W next to each other. Okay. And then we would take a linear combination of these. So for example, rather than taking one vector V, we can take some number of vectors Vi and some number of vectors Wj and just put them next to each other, Vi, Wj, and then multiply them by some scalar from the field. I showed that with Cij. So Cij is in our field. And then we can look at their sum, where this is a finite sum. So I'm assuming we are taking finitely many vectors in V and finitely many vectors in W. Okay. So it's just formal. You don't need to really assign a meaning to that. So for example, say some elements here, some elements in this space. For example, suppose the field F is R. Some elements would be, for example, V1 tensor W1, or 2V1 tensor W1 plus 3V1 tensor W2 minus V2 tensor W1. These are just some elements there. It's just like you're putting these elements in V and W next to each other. Okay, great. So we should define what is the addition, what are the vector space structures on this space to make this tensor product into a vector space. So if I take two of these things, if I take, for example, I have V1 tensor W1 plus 2V1 tensor W2 as an element inside this tensor product. If I take another element there, for example, V2 tensor W2 minus 3V3 tensor W3, if they ask me what is the sum of these two vectors, what is the sum? The sum is simply the sum. I just write these things next to each other. I just would write V1 tensor W1 here, plus 2V1 tensor W2 plus V2 tensor W3, sorry, W2 minus 3V3 tensor W3. I would simply just write these things next to each other, and that would be their sum. There is just a few things, a few rules which I should have in mind. So just like simple case of addition, everything is associative and the sum is commutative. But there is something more. There are three things which we should know. The first thing is that if I take a vector V1 and a vector V2 inside the vector space V, their sum would be another vector inside this vector space, right? And I can look at the tensor of that vector with another vector, say W1, inside the vector space W, okay? Now, the point is that this is, we want this, so the first rule says this is equal to V1 tensor W1 plus V2 tensor W2, okay? That's the first rule. The second rule is very, very similar, just the same thing for W. So I would just write the similar thing. Oops, sorry, there's a mistake here. It's W1. So we have something very, very similar here. Okay. The third one is about scalar multiplication. So if I multiply V1 tensor W1, the whole thing, if I multiply that by some number in the field, say we are looking at the field of real numbers, say I'm multiplying them by 2. It is equal to multiplying V1 by 2 and tensoring the result by W1, or multiplying W1 by 2 and then V1 tensor that. They are all of them supposed to be equal. Okay, so in some sense you can think about V1 tensor W1. It's kind of just like writing these two elements next to each other, V1 and W1. It's just we are putting them next to each other. That tensor doesn't do much more than that. But if you want to do that, you should understand there are small differences. What are those differences? So if I look at the first rule here, if I want to write that down using this notation, that would actually, the notation of V1 and W1, that would be slightly confusing. Why? Because if I say I'm just putting them next to each other, so if I say I'm writing V1 plus V2, and I'm just writing W1 on its right-hand side, and I would get a pair of the vectors, the first rule says that should be equal to V1 W1 plus V2 W1. Right? And that would be slightly confusing, because if you are thinking, that's the difference with ordinary product, because in ordinary product you might say this is equal to V1 plus V2 and W1 plus W1, which is 2W1. But that's not the case. When we are working with tensor product, that is not true. So in order to prevent this confusion, we are using just another notation. So this V1 tensor V2 is really nothing but just putting these two vectors next to each other. But because, as you can see, the rules of product and addition are different, especially addition, we don't use just this pairing. So that's why this notation is not a very good notation. And I'm not going to really use that because it's a little counterintuitive for us. Okay. So in another sense, if I want to finish the things I started, V tensor W, it has all linear combination of things like V I tensor Wj, right? And as I said, each Vi and Wj, they are very, very kind of similar to just putting these two things next to each other. The difference is just between these three rules I mentioned. And so this is kind of like V times W, because V times W is just also contains all these, this is by definition, V times W is the pair of elements Vi, Wj, and also all their linear combinations. But The difference is those three rules I mentioned. So if you take quotients by those three rules, actually this equivalence would hold. So it's kind of like we have the previous product, but we are applying these three rules. That's one way to think about it. Okay. Yeah, this is not exactly correct, so maybe I wouldn't go more into that. So having that in mind as the definition of tensor product, we can look at a few examples. For example, let's consider these. What is R tensor R over R? Okay, I should explain what does this over R mean. So R tensor R is just, we should use the definition we saw above, right? In one of the rules, we had this thing that CV tensor W is equal to V tensor CW, right? So this C is allowed to go from one side of the tensor product to the other side of the tensor product. Actually, this notation R here tells us what are the numbers which are allowed to go from one side of the tensor product to the other side. So when this number here is R, it means you're only allowed to, you can allow the real numbers to go from one side to the other side. For example, you wouldn't allow to do that with complex numbers. Actually here, because R, the things which appear in the tensor product, both of them are real numbers, there is no C, but later we would see that this would play a role. So let's start with that. What is this space? What is R tensor R? Does anyone know what is R tensor R? What is the answer to this question?
Just R?
Just R, that is correct. So let's see why that's true. So if we want to follow the definition, this is formal sum of things like Cij, Ai tensor Bj, where Cij are in the field, but the field is the real number. Ai is an element of R. Bj is also an element of R. Well, this is equal to, you see, Ai is a real number, so I can push Ai to the other side of the tensor product, right? So rather than writing Cij Ai tensor Bj, I can say Ai is Ai times 1. It's a real number, it's equal to itself times 1. And then I can keep 1 here, but send Ai to the other side of the tensor product, right? And I can do the same thing with Cj. Using this rule, actually, I sent Ai to the other side. So I can do the same thing with Cj. It would be sigma 1 tensor Ai Bj Cij. And then because all of these terms, they have 1 as their first component, the sum is only sum over the second component. So the sum should also come here, Ai Bj Cij. And these are just some real numbers. I'm just multiplying some real numbers and I'm adding them. I would end up with another real number, right? So the whole thing is just a real number. Let's just show that real number with D. So the whole thing is just 1 tensor D for D, a real number. So that's one way of writing this thing. I can write everything like that. any element in R tensor R, that's a better way of saying it. Any element in R tensor R can be written as one tensor a real number. And when you do that, when you write anything as one tensor a real number, you can just send that element to that real number, to D. Actually, it gives you a map. So any element in R tensor R can be written as one tensor a real number. And by sending that element to the second factor, you are constructing a map from that to R. Okay. Now, you should check that this is a linear map. You should check that it's surjective, which is kind of trivial, injective, etc. And when you do that, you would understand R tensor R is nothing really but just R. Okay, that's just it. Okay, let's look at the second question. What is C tensor C? So when I look at the C tensor C, I should decide over what field. C is defined as a vector space over itself, over C. It's also defined as a vector space over R. So if I suppose I'm looking at it as a vector space over C, and therefore the tensor product is defined over C, a very similar argument as we saw above showed this is nothing but C. Actually, R here played no role. It can be any field F. So any field, moreover, any field F, tensor F, over the same field is actually equivalent to itself. It's isomorphic to itself. But the point is that we can also think about C as a vector space over R, right? C is just like R2. And C tensor C over R is just is the same as R2 tensor R2 over R. And what is that? What is the result of this tensor product? Does anyone know?
Would it be R4?
Yeah, that's good. So what is the dimension of this? Remember, I told you the dimension of tensor product is equal to multiplication of dimensions. So the dimension of this thing is equal to 2 times 2, which is 4. And what is the vector space of dimension 4 over R? Well, that's
just R4.
That's just R4. That's correct. So it is equal to R4. Right? Okay. So there are slightly more complicated questions about computing the tensor product. I'm not going to continue that direction here. I want to go more towards what is called complexification. Is there any question about tensor product? Okay. So suppose we have a vector space V, a vector space over R. Okay, so it's a real vector space. Its complexification, which is usually shown by VC, it's called complexification. VC is a vector space over C. So what is this thing? This is just C tensor V over R. The tensor product is over R. What does it mean? It means all the elements are of this form. They are finite sum of things like this. This is supposed to be a vector space over C. So we would have some scalar here. I would show that with Cij. Because it's supposed to be vector space over complex numbers, Cij is a complex number, okay? And then I should have something from the first space tensor something from the second space. So the first space is C. Elements in C, they can be written as A plus IB. And I would use the index with I too. I hope you wouldn't confuse that. So A plus IB is something in, this is an element in C. And then we would have a vector V, where V is also a vector in our vector space. Okay. So the point is that the elements in this space, they can be, for example, of this form. They can be 2 plus 3i tensor V. And you know, anything like this, it can be written as 2 tensor V plus 3i tensor V, right? This is an example of one element in this space. Now, remember, the tensor is over the field R. It means only real numbers are allowed to go to the other side of tensor product. So 2 times V, 2 is allowed to go to the other side. And if it goes, we would get 1 tensor 2V, right? 1 tensor 2V plus. Look at the second term, 3i tensor V. 3 can goes to the other side, but I, the complex number, cannot go to the other side. So we would get I tensor 3V. And that's the thing, actually. Any vector in this space, anything in C tensor V over R, an element there actually would be something like this. Always you can write it as 1 tensor a vector, say V1, plus I, another vector, say V2. So anything in this tensor space can be written as this, just like what I did here, just like this. Just like the example we have above. We can always do that, right? Actually, this gives us a map from C tensor V over R to V times V. What is that map? Well, take an element here, take any, so let's show this map with T. I should define T of any element inside C tensor V. So some element inside this space. But I know any element inside this space is equal to 1 tensor V1 plus I tensor V2. Okay? I define T of that to be just V1 and V2. I would just write them in order. V1 first, V2 second. That's an element inside the vector space V times itself, V times V. And this map, again, is an isomorphism. So when we are tensoring a vector space by C, we kind of end up with V times V, kind of. So the point is that the right-hand side, for example, if V, just in our case, is a real vector space, the right-hand side still is a vector space over R. But the left-hand side actually is a vector space over C, right? For example, suppose V is just R2, right? For example, let's say V is R2. So the left-hand side would be C tensor R2 over R. The right-hand side would be R2 times R2, which is the same as R4. R4 is a vector space over R, but C tensor R2, you can think about it as a vector space over C. Why? So what does it mean to be a vector space over C? So I'm saying I can think about it as a vector space over C. This can be thought as vector space over C. Why is that? Well, you should pick an element there. Let's choose a random element there. I don't know. 2 plus 3i tensor, a vector space in R2. R2 elements in R2 are like 2 and 3. They are vectors like this. The point is that now I can, when I want to say this is a vector space over C, I should show you can have scalar multiplication by elements in C. So some element in C is, say, 2 plus I. Well, we can define this as scalar multiplication, right? I would just define this to be 2 plus I times 2 plus 3i. I would just multiply that number by the complex part of this thing. And I would tensor the result by the vector I had, which was, for example, 2 and 3 here. And this would be, say, 4 minus 3, which is 1, plus 6i plus 2i. So this thing is equal to just 1 plus 8i tensor 2 and 3. So I can just define the scalar multiplication with elements in C. So this process of multiplication can be carried over to a lot of things. So actually, if you pick RK and if you complexify it, it means tensor it with RK over R. The good way to think about it is not RK times RK. The good way to think about it is not RK times RK. So, for example, let's take it. I need to connect, sorry, my tablet. Let's just wait for a second. Okay, so for example, let's say K is equal to 1. So the good way to think about C tensor R is not thinking about it as R times R, which is R2. The good way to think about it is kind of as R2, but R2 as a vector space over C. What is that? What is, if I want to think about R2 as a vector space over C, what would that be? Yes, but it is correct, but it just has a name. If I want to think about R2 as a vector space over C, what do we call it?
C cross C?
No, it's just C. It is just C, right? R2 is two-dimensional plane, right? And C is kind of the same thing. So elements in R2 are of the form of A and B. Elements in C are of the form of A plus IB. And actually that gives a kind of identification between these two. So the way to think about C tensor R is not as R2. The correct way is to think about it as C. Also here, rather than thinking about it as R2K, the correct way to think about C tensor RK is CK. Okay, so here we have it. So C tensor RK over R as a complex vector space is isomorphic to CK. Okay, is it clear?
Yeah, I think so. I was just curious if For R cross R, or for R squared taken as vector space over C, why wouldn't you get like a vector space of the form A plus BI, C plus DI?
Okay, I did not get the question. Would you explain again what is the question?
Right. So if you were to take AB and multiply it by a complex number, then what would stop you from getting a vector of the form A plus BI, comma C plus DI?
Okay, I get it. So you see, I said R2 rather than R2, we want to think about this space as C. And rather than A and B, we want to think about it as A plus I, B, right? And then if we do that, the right-hand side would be a vector space over C. We can multiply things by elements in C. For example, if I take another complex number, C plus ID, I can multiply that by A plus IB. If I want to do the same thing on R2, it would be as, what is the product of C? Well, if A plus IB is A and B, then C plus ID would be C and D. And then the question would be, what would be the correct product on R2, right? Such that these two things would still be identified, they still would be equivalent. So if I do the multiplication on the right-hand side, I would see this is equal to CA minus BD plus I, CB plus AD. So here, if I want to stay on R2 but still have this product structure, I should define CD times AB to be CA minus BD as the first component and CB plus AD. And if I take this product structure on R2, then C and R2 are identified not only up to like having the same sum, but addition, but also having the same product structure. But we prefer not to do that usually. We prefer to go to C as a complex number, and then on C we have this natural multiplication, because on C I squared is equal to -1, and we can just use that here.
I understand. Thank you.
Yeah, good. Okay, so we have this complexification. So the first thing we understood is that C tensor Rk over R is just Ck. Now the point is that we can do the same thing, not just with Rk. Well, it's kind of similar, but we can do it with other vector spaces over R. For example, we have n by n matrices over R. N by the set of all n by n matrices over R. If we complexify this, we would get the set of n by n matrices over C. Okay. There are completely similar things, and you can prove all of them in the same way. Actually, all of them can be thought of as some Rk, these vector spaces, but it's also nice to write them more directly. Or you can think about well, this is not a finite dimensional one, but still it holds here. You can think about the vector space of polynomials in one variable x with real coefficients. If we complexify that, we would get polynomials in one variable x with complex coefficients. Okay, good. So we have these similar things, and you usually can guess them. On the other hand, as I said, when we have a real vector space V, when we complexify that with R, it is true that any element here, any element, can be written as one tensor some vector in V, like V1 plus I another vector inside V, like V2. So we get a actually direct sum decomposition. So we have one tensor, this vector space V, plus direct sum I tensor this vector space V. Actually, this is just a notation. It might be a little confusing. I just mean we would have two copies of this vector space V. Okay. So it's the same as V plus V. Now, this is interesting because this gives a natural inclusion of any vector space inside its complexification. So for example, if we have R2, if we complexify R2, well, let's start with R. If we have R, if we complexify R, we would get C, right? For example, and then think about C as this plane. Let's say this is C. Actually, there is a natural inclusion of the set R itself, the vector space R itself, inside its complexification. So R can be thought of as a subset of C tensor R. And actually, that's this subset. This is that the x-axis here, the real axis. You can think about it as the subset, as a subvector space R included inside its complexification. How does it work? Well, more accurately, we can think about V as a subset, subspace of C tensor V. How is that? This inclusion is not is a natural inclusion, but it's not really a set theoretic inclusion. What does that mean? So for example, you see, we can, a lot of times we think about R as a subset of R2, just like the figure we have here. It kind of looks like R2 and we have R inside that, right? This is the type of inclusion we have here. How does it work? Actually, any vector space V, which here we're talking about the real vector space, for any element V inside that, I can think about one tensor V. And one tensor V would be an element in this tensor space. So it seems as any element in V has a copy inside this tensor space. Sorry. Okay, we are recording, yeah. So it looks as any element inside V has a copy inside this vector space, right? So this is actually the kind of inclusion we have in mind. So this is not exactly correct. So the thing which is correct is that V is almost the same as, well, what is V? V is just the set of elements in V, right? Which we can think about them as just one tensor that element. Just write one next to that element for any element V inside V. And this one tensor V is a subset of C tensor V over R. Okay, so that's kind of a natural inclusion which we have here. And one of your homeworks, I think, is that one of the questions you are supposed to think about is this. If you have a map T from between two vector spaces over R, V1 and V2, which is, this map is linear, but when we say linear, we mean linear with respect to R. Actually, this induces a linear map over over the complexified spaces. So for any linear map between two real vector spaces over R, we would have a linear map. We would call it complexification of the linear map between the complexification of these vector spaces. And this map would be linear with respect to C. Okay. How does it work? Well, let's look at an example. So suppose we have a linear map from, say, R2 to R2. Just suppose we have something like this. Suppose we know T of 1 and 0 is, say, 2 and 0, and we know T of 0 and 1 is 0 and 1 over 2. We just defined our linear map over the basis, right? Now we can look at the complexification of everything, right? If we complexify R2, we would get C2. So we should have the complexified map from C2 to C2. I want to know what is this complexified map is from C2 to C2. So I should be able to define this thing over any vector in C2. What is any vector in C2? What is the vector in C2? Well, it has two components. Both of them are complex, right? So for example, it would be something like 2 plus I and say 3I. Let's just take an example. I want to know what is the image of this one in C2. Well, we know that 2 plus I and 3I, this vector, is actually equal to 2 plus I and 0 plus 0 and 3I, right? I can write down this vector as sum of two other vectors. I can actually simplify that a little bit more. 2 plus I and 0 is 2 and 0 plus I and 0 plus 0, 3I. I can actually continue. I can bring the scalars out of the vector. So it would be 2 and 1, 0 plus I, 1, 0 plus 3I, 0, 1. What is the image of 1 and 0 under this map T? Well, we know 1 and 0 goes to 2 and 0. Look at the definition of our linear map up there. Well, it's a linear map. If 1 and 0 goes to 2 and 0, then 2 times that would go to 2 times 2 and 0 plus. I would keep I outside, just like it's a scalar and the linear map doesn't care about that, right? And 1 and 0 also goes to 2 and 0. Plus 3I, 0 and 1 goes to 0 and 1 over 2. Well, we can compute this and add them together again. It would be 4 plus 2I plus 0, 0 plus 0 plus 3I over 2, which is equal to 4 plus 2I and 3I over 2. So that would be the image of this map we started with, 2 plus I and 3I, right? So as you can see, we found a way to compute the value of T on something in C2, right? Actually, in the same way, we can compute T, complexified T, on any vector in C2. And we should show this is going to be a linear map now, but linear with respect to C, right? And it was kind of obvious from beginning, right? Because what does T do? Look at T. T multiplies the first component by 2. 1 is multiplied by 2. And divides the second component by 2, right? So 0, 1 goes to 0 and 1 over 2. That's exactly what this complexified version also does. Multiplies the first component by 2, so 2 plus I should go to 4 plus 2i, and divides the second component by 2, so it should be 3i over 2, which is what we got at the end. So it kind of doesn't care if you have a real number or complex number. It does what it does when it's defined over the real numbers. Maybe I should just mention two important theorems. One is that when we have a vector space defined over R, we can look at its dimension over R, right? It's something. For example, let's say the dimension of V over R is n. And then we can look at the complexified version of this vector space, say VC, and then we can look at its dimension over complex numbers. And the point is that these two things are equal. So for example, let's just look at an example in order to prevent any confusion. So for example, suppose V is R2. The dimension of R2 as a real vector space is 2. The complexification of R2 is C2. It's correct that you might say that if you think about C2, you might say C2 is, well, C is like R2, so C2 is like R2 squared, which is R4. And you might say that's 4-dimensional. But that's the dimension over real numbers. What this theorem is talking about is dimension of C2 over the field of complex numbers. And over complex numbers, C2 is still 2-dimensional, and these two numbers are, in fact, equal to each other, right? So we still have this equality. This equality is correct. That's one thing. The other thing which I want to say, and maybe we would finish today's class, is that when we have two, say, vector spaces over R, V1 and V2, and we have a linear map between them, say T, we can look at the complexification of these two vector spaces, V1C and V2C. And as I mentioned, there would be a complexified linear map between these two. On the other hand, remember, any vector in V1, let's say V inside that, you can send it to one tensor V to get a vector in one V1C, the complexified vector space. So this would actually gives you a map from V1 to V1C. It gives you a map from this one to this one. Similarly, we have a map from V2 to V2C. And we say, actually, this diagram commutes. And this is the notation. What does it mean? So if I show the first map, let's say by, I don't know, let's say show it with I1 and the other one with I2, it means if you start from here with V1 and first go to V2 using T and then come down using I2, the map you would get is the composition of these two maps, and that's I2 combination with T. Now you could start from V1, but rather than using T, you could use I1 and come down here and then use TC to get to the same destination. So that is TC I1. And the fact is that these two maps would be equal. So if you start with an element here in V1, doesn't matter which path you take, you would end up at the same points. That's what it means to say this diagram commutes. And that's correct for complexification and these inclusion maps. Okay, maybe it's a good place to start the class. Stop the class. If you have any question, you can ask now.